Hey everybody, in this video we are going to talk about a concept known as spontaneity. Spontaneity is simply a condition where a process moves forward without any additional inputs of external energy. Let's take, for instance, gravity. When a person wants to slide down a slide, the person will slide down the slide without any external energy, or in this case, without any external help. So for example, the person doesn't need someone to push the person down the slide in order to slide down the slide, because the person can do it on his or her own because it is a spontaneous process. And this is related to gravity because gravity is a force that's, making this process possible. It's pushing you down closer to Earth. And that's what gravity is, because if you throw a rock up, it will fall back down due to the forces of gravity. Now let's relate this concept to chemistry. A spontaneous reaction is a reaction that, once given enough energy to overcome the activation energy, will move towards equilibrium without any other external energy. And note that the direction that the reaction will be spontaneous will be forwards, as we will see soon. Let's take, for example, the combustion of methane. We know that methane is CH4 plus O2 becomes CO2 and H2O. Now, balancing the reaction is not as important here because we are thinking about what's going on. So we all know that when we burn something like methane, which is a fuel, we know that it will continue to burn until it runs out. So this is like a Bunsen burner. And we know that in Bunsen burners, the methane gas that is released from the valve will continue to support this reaction until it runs out, of course. So this means that without any external help, the reaction continues happening until either there's no more methane gas or there's no more oxygen gas. So because of this, the combustion of methane is a spontaneous process, since after you give it like a spark, then the reaction will continue moving forwards without any other external energy. And in this case, the spark that you add in order for this reaction to start happening is known as the activation energy, since the spark was like the minimum amount of energy required to activate the reaction. And after that, the reaction just keeps on going on and on, showing that it is a spontaneous process. Now, a spontaneous process can happen super fast or super slow. Either way, as long as the spontaneous reaction moves forward, then it is a spontaneous reaction. So let's take melting ice, for example. We know that when we melt ice, the solid form turns into the liquid form. And in this case, we know that even though this might happen not that quickly, it still happens. And because of that, this process is spontaneous. Now, what about rust formation? We all know that when you put iron or some metal outdoors, it will slowly react with oxygen to form rust. And in this case, the rust you see there is iron 3 hydroxide. So we all know that rust will happen eventually, but we know it's a super slow process. Even though it's a super slow process, it still moves forward and it still happens. And because of that, this is still considered a spontaneous process. Now let's take a look at what non-spontaneous reactions are. So, in a non-spontaneous reaction, reactions will not go forward spontaneously. Instead, their backward reactions are spontaneous. So, this might be a little confusing, but let's take a look at this example here. In this reaction, liquid water is becoming gaseous water, and this is known as vaporization. but we're saying that it's happening at 90 degrees Celsius. But we know that the boiling point of water at 1 atmosphere and under normal conditions is 100 degrees Celsius. So do you think this reaction will be spontaneous? Will we see water boiling off under the boiling point? Well, no, because, for example, you could easily see this by, for example, putting water in an environment that's under the boiling point, such as maybe 25 degrees Celsius, which is room temperature. At room temperature, do you see water spontaneously boiling off? Well, no, and that's because it's not a spontaneous reaction. So any reaction that's under the boiling point will not occur, and in this case, the reaction I'm talking about is vaporization. So in this case, at 90 degrees Celsius, this reaction will be non-spontaneous. Now that's the forward reaction. What about the backward reaction? What about this reaction here? And this can also be rewritten as this. Now this reaction, or this reaction, will most definitely be spontaneous. Now let me explain why. So this is talking about the conversion of gaseous water into liquid water at 90 degrees Celsius. So we had a bunch of gas, let's say in a container, and this was all water vapor, and it was at 90 degrees Celsius, which is under the boiling point, then we will predict that this water will condense because under the boiling point, things like to stay liquid. And because of that, gaseous water or water vapor will become liquid water. And that's why this process of gaseous water turning into liquid water is actually a spontaneous process. So from this, we learned that while the forward reaction might be non-spontaneous, the backward reaction will most definitely be spontaneous under the same conditions, of course. And this also applies to the spontaneous reactions we've looked at. Let's take a look at the kid that's sliding down the slide. So, the kid sliding down the slide from the top to the bottom was established to be a spontaneous process. Now, what about the opposite process? The process of going from the bottom of the slide back to the top. Now, as we've established, this is a non-spontaneous process, and we can explain this by thinking about what the kid would do to get back up the slide. So this kid would not be able to just sit on the slide and go up without any external forces or any external sources of energy. So if this kid sat down here, he or she would need help. How would the person get help? Well, the person could have person B push the person up the slide, and that would be considered an external source of energy. Or this person could use the hands and the legs to move up the slide by climbing it. But this is using muscles, and using muscles is a source of external energy because you're not doing it without any additional inputs. Your additional inputs are your muscles, and that's not considered a spontaneous process. Instead, whenever you go from the bottom to the top of the slide, it is considered a non-spontaneous process because you have to input things that you wouldn't have to when you're going from the top to bottom, such as your muscles or maybe a friend. So, let's move on to another topic. Let's relate everything we've talked about to the idea of equilibrium, which is what we covered in the previous unit. So I'm not sure why there's a layer, but there you go, I fixed it. So let's connect this topic to chapter 10. Let's first note that reactions that are moving towards equilibrium are spontaneous, while reactions moving away from equilibrium are non-spontaneous. This is because nature really wants reactions to go towards equilibrium, because remember, equilibrium is the ideal condition that everything wants to be at. So going towards it would be ideal and thus would be spontaneous. Meanwhile, moving away from equilibrium would be non-spontaneous. So let's think about this in terms of Q and K. When Q is less than K, or when the concentration of products over reactants, or Q, is less than K, or when there are too little products, the reaction will move forward to reach equilibrium. The forward reaction is a spontaneous reaction, while the backward reaction is non-spontaneous. So if we have too little products, then that means that the reaction will want to go forward to produce products. So, for example, if we consider A as our reactant and B as our product, and if Q is less than K for this reaction, then this reaction will want to go forward to produce B. And this would be a spontaneous process since we know that this is going to happen since the reaction is moving towards equilibrium. Now, what about the opposite process where B becomes A? Now, we all know that this is not going to happen because the forward reaction was established to be spontaneous. We know that this process is moving away from equilibrium since we established that Q is less than K, so the reaction should be moving forward and not backwards. So if it wants to move backwards, that's not going to happen because it's moving away from equilibrium, so therefore this process is non-spontaneous. Now let's talk about the opposite thing, when Q is greater than K, or in other words, when there are too many products. When this happens, the reaction will move backward to reach equilibrium. And this is because if you have too many products, it will want to give up some of the products and give it back to the reactants in order to reach equilibrium. So remember, everything wants to reach equilibrium. The forward reaction is a non-spontaneous reaction because, as you can see, this clearly wants to go backwards. So this reaction over here would be the spontaneous process, while the forward reaction would be non-spontaneous because that's not the direction where equilibrium wants to go. So now that we've gone over that, let's talk about how we make non-spontaneous processes happen, because they do happen sometimes. So how do we make non-spontaneous reactions happen if equilibrium favors the reverse process, which would be the spontaneous one? So that's a problem, because in this case, we're trying to force a reaction to move away from equilibrium if we're causing a non-spontaneous process. Since if we remember, a non-spontaneous reaction moves away from equilibrium. So how can that happen? How can we defy the laws of nature? Well, we could actually couple a non-spontaneous process with a spontaneous process. So for example, the process going from A to B is non-spontaneous, for example, and does not want to go forward. But on the other hand, this reaction C to D is very, very, very spontaneous. It really, really wants to move forward. Now, if you combine these two together, you get a reaction that's kind of spontaneous. It's like an average of these two. And overall, it wants to move forwards. Not very, very wants to go forwards, but just wants to go forwards. So if you look at this, you might be thinking Hess's law, and you're absolutely right. And we will go over Hess's law in relation to spontaneity in videos in the future. So technically, this reaction A plus C becomes B plus D is an entirely different process. But we only care about A turning into B. So as long as A turns into B, no matter if other chemicals get involved, we can say that we successfully made the process of turning A into B spontaneous. Now, the second way to drive a non-spontaneous reaction forward is through external energy. So, remember the kid on the slide? Well, the kid on the slide, if the kid wanted to get back up the slide, the kid would need to input some external energy for that to happen. So, this is the same exact idea over here, where we have a reaction that won't want to happen unless some external energy is applied. So in this case, I chose this reaction, water turning into H2 and O2 gas. We know that in nature, when we have a cup of water, it's not going to spontaneously give off O2 and H2 gas, because I don't think that's a thing. Instead, this reaction would be considered non-spontaneous, since we don't observe it happening spontaneously in nature. Because of this, this reaction would be non-spontaneous, as I said. So how do we drive this? Well, electrolysis. Now, we will learn about this in Unit 13, but basically what electrolysis means is that you put electricity into the system and you force the water to split into H2 and O2 gas. Now, if you know this, electro means electricity, and lysis means breaking things apart. So in this case, we're using electricity to break apart water. Now, we know that this process is not spontaneous. So, we can use a battery. A battery is an external source of energy that provides electrical energy. So, this electrical energy can actually force this non-spontaneous process to go forwards and happen. Note that adding an external energy does not necessarily make this process spontaneous. So let's take a look at this analogy that's also related to gravity, incidentally. So we all know that due to gravity, water will flow down a straw. But if we sip on the straw, and you sipping is a source of external energy since you're forcing the water to move up the straw, and that's using your breath, your muscles, and that's all external energy. So if you sip on the straw, the water is forced up the straw, and we know that forcing water up a straw is a non-spontaneous process that's possibly driven by some external energy. So note that you did not make water flowing up a spontaneous process by doing this. You're simply forcing a non-spontaneous process to happen. If you did make water flowing up a spontaneous process by simply sipping on it, then all the water in the oceans and across the world would suddenly start moving up the sky. And you don't have that type of power because you're not an omnipotent person. So therefore, you cannot cause non-spontaneous processes to become spontaneous by adding some external energy. So just remember that. And now let's take a look at this. What happens if a reaction is neither spontaneous nor non-spontaneous? In other words, what if a reaction doesn't want to move forwards or backwards? The simple answer is that the reaction is at equilibrium. Now, let's do a little review from Unit 10 and Unit 9. In Unit 10, we said that at equilibrium, the reaction quote-unquote stops because the forward and backward reactions happen at the same rate and cancel each other out. So the rate of forward is equal to the rate of backwards, and they cancel each other out so nothing happens. Now, what if a reaction moves forwards spontaneously? Well, if a reaction chooses to move forwards, we know that the rate of the forward reaction would be greater than the rate of the backward reaction. So overall, the forward reaction dominates and the reaction will move forwards. Now, what about if a reaction wants to move backwards? Or in other words, the backward reaction is now the spontaneous process and the forward reaction is the non-spontaneous process. So if a reaction moves backwards, we know that the rate of the forward reaction will be less than the rate of the backward reaction, leading to the rate of the backward reaction dominating, and as a result, the overall reaction will go backwards. Now, of course, at equilibrium, Rf is equal to Rb, and nothing happens overall. So remember, this accentuates how reactions are dynamic, meaning that the forward and backward reactions happen at the same time, but not necessarily at the same rate as we see over here. Now let's review some things about catalysts and this other concept I want to introduce known as inhibitors. We all know that catalysts speed up the forward and backward reactions equally. Therefore, catalysts do not change the direction of the reaction, since if, for example, the forward reaction was faster than the backward reaction to begin with, or in other words, the net process is that the reaction will move forwards overall, then multiplying each reaction rate by the same factor, which should be greater than 1 by the way, and this would speed both processes up equally, won't change the fact that the reaction is moving forward. Instead, the forward reaction is now faster than ever because of the catalyst. So let me show you how that works by giving you an example. So in this case, we see that the process of A turning into B has a forward rate of 5 moles of B per second. So 5 moles of B are being produced every second. Now the backward reaction actually wants to take away some of that B and turn it back into A. So the rate of the backward reaction would be -1 moles of B per second, because this reaction is taking away B, so that's why it's negative. So if you add these two processes up, the overall process is that 4 moles of B are being produced per second. So the forward reaction wins, and thus the forward reaction is the spontaneous one. Now, what happens if we add the catalyst? Does this change spontaneity? Does this change the position of equilibrium? Well, let's find out. So with a catalyst, we will multiply both of these by the same factor. So I multiply both of them by 2 for simplicity. And we see that the overall reaction rate is 8 moles of B per second. So A to B wins. So the forward reaction wins again. But look at this, it's faster than before. Therefore, catalysts do not change the equilibrium position of the reaction. In this case, the reaction is still shifting to the right. Therefore, catalysts do not change the spontaneity of the reaction, since the forward reaction remains the spontaneous one. So notice that by adding catalysts, you are not changing the direction or the spontaneity of the reaction. Now, inhibitors are something you probably haven't heard of before, but it's a very simple process. Instead of speeding up reactions, inhibitors actually slow reactions down. So it does the opposite of what a catalyst does. Nevertheless, both catalysts and inhibitors simply change the speed of an overall reaction without impacting the spontaneity, or in other words, the direction that equilibrium wants the reaction to go. So this is something that I felt like we had to go over in order to fully grasp the concept of spontaneity. Now let's do a few practice problems. I want you to label each reaction or reactions, depending on if there's more than one reaction going on, as spontaneous, non-spontaneous, or at equilibrium. Let's look at A, the reaction that TNT undergoes when it explodes. Most of us know if we play Minecraft that TNT wants you light up with a fuse, so that fuse would be the activation energy. And the moment that you light the fuse, the TNT will spontaneously explode without any external help. So, it will explode, there's a gigantic cloud, and therefore, the reaction that TNT undergoes when it explodes will be a spontaneous process, even though you added some external energy at the beginning. But we don't really count that. So, let's talk about B, the very slow decomposition of hydrogen peroxide into water and oxygen gas. So, even though this process is very slow, it's still decomposing. The H2O2 is still decomposing into these two things. So, it's still moving forwards, and we don't care about speed when we talk about spontaneity. so therefore this process is also spontaneous. Now, let's talk about C. I want to know if the reactions occurring at point C will be spontaneous, non-spontaneous, or at equilibrium. So from previous units, we know that if a point is on the curve of a phase change diagram, we know that those points will be at equilibrium. So in this case, this is actually the triple point, where the solid, liquid, and gas are all at equilibrium with each other. So guess what? This is actually at equilibrium. Now let's talk about D. A solid is undergoing a reaction at this point over here. So let's label our regions solid, liquid, and gas. So we placed a solid at this point. What do you think will happen? Well, first off, in this place, we know that things like to be gases because at point D is where gases exist. So, if we have a solid undergoing a reaction at this point under certain pressure and a certain temperature, then we know that the solid will naturally want to become a gas because at this point, everything wants to become a gas. But guess what? You have a solid right here, so naturally it would want to become a gas at that point. And because of this, because it's a natural process that's going forward without any external help, then this process would be spontaneous. So before we end this video, I want to remind you that a spontaneous reaction is a reaction that, once given enough energy to overcome the activation energy, will move towards equilibrium without other external sources of energy. So note that even though a reaction might need some energy or external energy at the beginning, once you give it this energy, the reaction will move on and on without any other sources of external energy. So, for example, the sparks used to start the combustion reaction for methane is considered an external energy needed to overcome the activation energy. But once this happens, the reaction will move forwards spontaneously. And this goes the same for this kid that wants to slide down the slide. For the kid to slide down the slide in the first place, the kid has to climb up the stairs. Or in this case, it's a ladder actually. So the kid climbing up the ladder would be the activation energy required for the spontaneous reaction to start. So don't get activation energy confused when considering whether a reaction is spontaneous or not, because in both spontaneous and non-spontaneous reactions, reactions need a certain activation energy in order to start. So that's all I wanted to do for this video. I hope you learned a lot and have a nice day, everybody.